Okay, so today we're going to be finishing up chapter 26. This is our last lecture before the midterm. This is the last content that we'll learn, the last new content that will be covered on the midterm. Okay, and then just some other general midterm studying and how to do well on the exam things. So like I said, it will cover chapters 21 through 26. The most important thing to do is go over lecture and discussion problems. So make sure that you are familiar with and know how to do all of the problems that we did in lecture. And then once you're comfortable with those, then go on to discussion problems. And make sure you can actually do the problems. So this is like the number one trap that, like studying trap that students fall into, is that they look at the problem with the solution in front of them and then say, okay, I understand this solution, so I'm gonna go on to something else. But then when the exam comes and you have to actually reproduce that solution, then you realize like, oh, I don't actually know how to do it. So make sure that you actually do the problems. Don't just like read the solutions or just read the book. You have to actually practice, just like playing the piano. You wouldn't expect to get good at playing the piano by like reading a book about it. So you have to actually practice problems and get like muscle memory for these problems. And then the other thing is make sure you can do the problems in a reasonable amount of time. So pick like 4 or 5 lecture problems, put a timer on yourself, and see if you can actually do the problems in an hour. I know it's also really nerve-wracking with Canvas. There's like a timer on the screen, so you like watch your time tick away, which would freak me out if I was a student. So get used to like timing yourself if you suffer from that kind of anxiety, and just put your like timer so that you're used to now solving problems watching a timer. I've had a lot of students come to me and they're like, oh, I studied so much, but like I still did poorly on the exam. And when I talk to them a little bit, it turns out that it would take them like an hour to solve each problem. It's like, well, if it's taking you an hour to solve each problem, like, yes, you can do it, but you can't do it on an exam then. So make sure that you can solve them in a reasonable amount of time so that you can do all of the problems on the exam. Okay, and then another trap that people fall into is if there's a concept or a topic that is not making sense to you, don't just watch a bunch of YouTube videos about it and hope that it will eventually like click, or think that watching 5 hours of YouTube videos is equivalent to 5 hours of like doing practice problems. That's not really efficient studying. Even if you just watch my lectures a bunch of times but don't actually do the problems, that's not going to really do anything for you. So you have to be efficient and effective with your studying, and the best way to do that is by actively doing problems. Like I said, you could watch 5 hours of how to play the piano on YouTube, and you're not going to know how to play the piano at the end of those 5 hours. So just make sure that you actually do a lot of problems. That's the best way to learn. Okay, so now we can get into the topics for today. So far, we've only been doing steady currents and circuits where we have the same current moving and it's not time dependent at all. So now we're going to look at time dependent currents. And we're going to introduce this time dependence by looking at circuits that are capacitors and resistors in series. So this is how we're going to achieve this time dependence. So the first thing we do is we look over here. So here we have an open circuit because we have this open switch here. So part of the circuit is not complete, so there's no current that can flow through this since it's not a closed path. So we have this open switch here and nothing's happening. So it's important to note also that this capacitor has no charge on it. Since we don't have a full circuit and there's no current flowing, that means no charge has built up on this capacitor, so it has 0 charge right now. Then what we're going to do is we're going to close this switch so it is a complete circuit. So we're going to close this, and we're going to call that t equals 0. So the instant that we close that switch, that's t equals 0. So now at t equals 0, that second right when we close the switch, current can now begin to flow because it's a closed circuit, and current will immediately begin to flow. So at t equals 0, our capacitor is still not charged. So current is flowing now, but it only just started flowing, so no charge has built up on this capacitor yet. So our capacitor is still at Q equals 0. So that means that the potential difference over this capacitor is also 0. So we'll call that VBC is also 0 because there's no charge on this capacitor. It basically just looks like sort of just straight wire with nothing in it to the circuit. But then we can look at over the resistor. So remember, current is flowing. Current just started flowing. So over this resistor now, it will just look like current flowing through a regular resistor. And we know the potential over, just a regular resistor is given by Ohm's law. So the potential over this resistor is equal to the EMF supplied by this battery. which is equal to the current times the resistance. And this here, I wrote I naught because that's the initial current. That's the current that starts flowing at time t equals 0. And then we can write the initial current, we can also rewrite as the EMF over the resistance of that resistor. Okay, so this is the initial current. So now sometime later, so now, maybe a minute or two later, the capacitor has now fully charged. So enough charge has built up on this capacitor that it's now at charge plus Q and minus Q on each plate. So since now all of the charge has built up on this capacitor, there's no more current flowing. You can basically think of it as all of the charge that was previously making up the current has now collected on the plates of the capacitor, and they're not going anywhere anymore. They're not moving around this circuit. They're just sitting on this capacitor plate. So we'll call this T is not equal to 0, so just later. So the charge on each capacitor is not equal to 0 anymore. We'll call this Q final. So the magnitude of the final charge on your capacitors. The potential difference across the capacitor now, so VBC, is now no longer equal to 0 because now we have a regular capacitor that has an electric field between it, which means it has a potential. So the potential between these plates is now equal to the potential difference or the EMF supplied by the battery. And now the potential difference over the resistor is now 0 because there's no current flowing through it. So the potential difference over the resistor is now 0. Okay, and then the final current through the circuit, as we said, is 0. So there's no more current flowing through this circuit. So let's just recap what happened. So we call this charging a capacitor because the capacitor goes from 0 charge to now its full charge. So when we charge a capacitor, the first thing that we did was the switch was initially open and no current was flowing. Then we close the switch and current immediately begins to flow around the circuit. So that means the voltage over the resistor initially, the second we close the switch, is just equal to the EMF provided by the battery. We just use the V equals IR. So this is just equal, the potential drop over here is just equal to the EMF of the battery. And the potential difference over the capacitor is 0 since it has no charge on it. So then, as the capacitor charges, more and more charge builds up on the capacitor. The voltage on the capacitor increases. The voltage drop over the resistor decreases down to 0 eventually. So that means that the current through the circuit is decreasing. And then when the capacitor is fully charged, we have the potential over the capacitor is equal to the EMF, and the potential difference over the resistor is equal to 0. And no current is flowing anymore. So let's figure out how to write the charge that's building up on the capacitor as a function of time. So the first thing we can do is we can use Kirchhoff's rule and basically write an equation for the potential through the whole circuit. So the first thing we meet is we go over this battery. So we pick up a positive EMF. Then we go over the resistor. The resistor will have a potential, it will be minus IR. So we'll have a minus IR. And I'm writing a lowercase I. The lowercase I refers to the time-dependent current. So this is really a function of time here. So minus IR. And then the capacitor will be minus Q over C, right? Because we have the potential for a capacitor is Q over C. And the lowercase q also refers to a time-dependent charge. So both I and Q here are functions of time. And then this is all equal to 0, because then when we keep going around our loop, we get back to the battery. So now let's take this equation. This is just a general equation here. And let's look at the specific time at t equals 0. So at t equals 0, we know that the charge on the capacitor is also equal to 0, right? So let's write that again. So at t equals 0, this term is 0 because there's no charge on the capacitor. So all we have is that the EMF is equal to the current times the resistance. And we said at t equals 0, we will call that current I naught. So I'll change this to I naught. And then, as we did before, we can just rewrite our initial current as the EMF over the resistance. So let's keep this equation in mind. And now let's look at the case when t is not equal to 0 and the capacitor is fully charged. We'll say the time dependent, the charge on the capacitor is equal to the final charge. So we said when the capacitor is fully charged, there's no more current going through the circuit. So this equation will now become, this term is 0, so this equation will now become E is equal to Q over C, but the Q here is the Q final, so I'm going to write Q final. So the Q final we can write in terms of the EMF of the battery and the capacitance of the capacitor. So we have these two equations, and we kind of knew these already, but just to check that everything works out. So now what we're going to do, now it might not seem obvious why we're doing this at first, but hopefully at the end maybe it will. So I'm going to just rewrite so that we have our equation up here. So we have E minus IR minus Q over C is equal to 0. Now I want to get I by itself and just write an equation just for the time-dependent current I. So I'm just going to get I by itself here. So I'm going to have IR is equal to the EMF minus Q over C. And now I can divide both sides by R so that I get I by itself. So I have E over R minus Q over RC. Now, what I'm trying to do is I'm trying to get an equation. I'm trying to get Q of T. I'm trying to get the equation that describes how the capacitor is charging, how the charge on the capacitor is changing with respect to time. So remember that we said that the current is equal to dq dt. So remember, current is equal to the time derivative of charge. So I can rewrite this little I here as dq dt. So that's equal to E over R minus Q RC. Now what I'm going to do, so I'm going to do a little bit of algebra that may not be obvious at first. So I'm going to pull out the negative and the RC. So I'm going to factor out a negative 1 over RC from this. So I have negative 1 over RC. And then I'm left with Q minus C times E, right? So if I factor this, if I multiply this back into here, I'll get this equation. So I just factored out a negative 1 over RC here. So now what I can do, so this is equal to dq dt. So now what I can do is I can do separation of variables to solve for Q. So that just means I'm going to get my Q on one side and my T on the other side. So I'm just going to divide both sides by this. So I'm going to get dq over Q minus CE. And then I'm going to put my dt on the other side. So I'm going to have negative 1 over RC dt. And now I need to integrate. So let's just bring this equation over here. So now I need to integrate this. So since I want to just find a general term for Q of T, I'm just going to integrate both sides from 0 to some random Q, and then from 0 to some random T. And I just put little primes on my variables of integration to just distinguish them from some final Q and some final T I'm integrating to. So this term here comes out to, if you integrate, you get ln Q minus CE, and we're evaluating from 0 to Q. So this becomes ln Q minus CE minus ln of negative CE. So I can rewrite this as ln Q minus CE over negative CE. So that's my left-hand side of the equation. So I'll label this, this is the left-hand side. So my dt side is just negative 1 over RC. I pulled the constant out, dt. So this just becomes negative 1 over RC times t. So this is my right-hand side. So now I can set these two equal to each other again. So I have ln of Q minus CE over negative CE, and then I have that equal to negative 1 over RC times T. So now what I want to do is, this equation is really not that nice. Since I want to get Q by itself, I want to just have like Q of T is equal to some function of T, and this isn't it. So what I have to do is raise both sides to the power of E to get rid of my ln. So I'm going to raise each side to e to that power, and then that will cancel. E to the ln of something is just that something. So this side becomes Q minus CE over negative CE, and then this becomes E to the negative T over RC. So now we're almost there. We just have to get Q by itself. So I'll write that, I'll do that over here. So I'm going to multiply, I'm going to get this over to this side. So I have Q minus CE is equal to negative CE times E to the negative T over RC. And then I'm going to move this negative CE over to this side. So I get Q is equal to positive CE minus CE E to the negative T over RC. Then I can just rewrite it so it's a little bit cleaner by factoring out the CE. So I just have 1 minus E to the negative T R over C. And this is my equation for Q now. So this is how you find the time-dependent charge on a capacitor as it's charging in an RC circuit. So I just rewrote that here. Now I swapped out the CE here. So if you remember, initially we said that the final charge on the capacitor is equal to the EMF of the battery times the capacitance of that capacitor. So I just rewrote this CE here is just Q final. So the charge on the capacitor is just Q final, and then times this term, which is dependent on T. So just to go over these variables here, we have QT is the time-dependent charge on the capacitor. QF is the final charge on the capacitor. E is Euler's constant. It's not Euler. Then T is the time. R is the resistance in the resistor, and C is the capacitance of that capacitor. So now what we need to do is find a similar equation for the current as a function of time. So we want to find how does the current depend on time as this capacitor is charging. Now you might say, well, we had an equation for that already. We had this, right? That's how we started, sort of. But remember that this and this are both functions of time. And the way we had it written here, this isn't an explicit function of time, because where's your variable t, right? T is hidden in this Q of t here, and we didn't know how this depended on time yet. So now that we did find that, right, we found that Q of t is equal to this, you can just plug this equation for Q of t right back in here and find your equation for I of t. Or, so that's one way to do it, and you'll get the same answer. Or you can just take the derivative of this equation and say, well, I know that the time derivative of the charge is equal to the current, so I'm just going to take the derivative of this with respect to time, and you'll get the same answer. So I'll just do the derivative way to show you. So I had Q is equal to CE, 1 minus e to the negative t over RC. So I can just take the derivative of this whole thing. So the time derivative of this term is 0 because it's just a constant. So then I have negative CE e to the negative TRC, and I'm taking the derivative of this with respect to time. So this comes out to, when we take the derivative of e to the negative TRC, t over RC, we get a negative 1 over RC, and then we just have negative CE e to the negative t over RC. So we can see that our negatives cancel, our c's cancel, and we're left with e over r, e to the negative t over r, c, and then e over r we said was our initial current. So we can just rewrite our current as a function of time as I naught e to the negative t over RC. So now this is our time-dependent equation for the current. Okay, so I just rewrote that here. So this is the current as a function of time as the capacitor is charging. And then we have all of our variables listed here. So now just let's look at the difference between these two formulas. So this is the current. And this is the charge. So the current we can see is an exponential decay. So it starts at t equals 0, it jumps up to its maximum value, and then it decays exponentially. The charge, on the other hand, starts at 0 and then gradually increases to its final charge here. So this is the difference between these two equations. One is decreasing with time, one is increasing with time. So now let's talk about the time constant. So when we have this factor of e to the negative t over RC in both of our equations, this denominator here is called the time constant, and it's denoted by tau. So the time constant just tells you how long it takes the current to decrease by a factor of e. So when your current has decreased to I naught over e, that time is R over C. R times C. And then similarly for the charge, when the charge has increased to QF over E, that time is RC. So the time constant just tells you how long or how slowly a capacitor charges or how fast it charges. So if we have a small time constant, it will charge more quickly. And then if we have a big time constant, it'll charge more slowly. So now we get to discharge our capacitor. So we charged it up, and now we want to discharge it. So how do we do that? So it's sort of the same thing we just did, but in reverse, obviously. So now we take out our battery because we're not charging it anymore. So we remove our battery, and we replace our battery with this open switch. So our capacitor is totally charged, and we don't have a full circuit yet. So we have this open switch, then we close the switch. So now the moment that we close that switch, we'll call that t equals 0 now. Our capacitor is fully charged. So the charge on our capacitor, we're going to call Q naught. And now this is a little bit confusing because we're looking at these as charging and discharging a capacitor as like two separate things. So now since we're starting with a fully charged capacitor, we're calling it Q naught because now it's our initial charge. But like these are sort of the same thing. The final charge when you're charging a capacitor is the same as the initial charge when you're discharging it. So then sometime later, when our capacitor now is fully discharged, the charge on our capacitor is 0. So when t is no longer equal to 0, sometime later, the charge on our capacitor has gone down to 0. So now we're going to have to write equations for the time-dependent charge and the time-dependent current for discharging our capacitor, just like we did for charging our capacitor. So let's look at find an equation for the charge first. So to find the time-dependent charge, let's go back to that equation we had that was I over equals E over R minus Q over RC. So this was from our original Kirchhoff's law that we wrote. So now when we discharge a capacitor, notice we removed the battery, right? So that means there's no more source of EMF. So this term is now 0. So our equation now is just I is equal to negative Q over RC. So we do the same thing. We convert I to the derivative of charge with respect to time. So dq dt is equal to negative Q over RC. So now I'm going to do separation of variables again. So I'm going to have dq over q is equal to negative 1 over RC dt. And I'm going to integrate both sides. But now I have to be a little bit careful with my limits of integration because my integral is starting at a fully charged capacitor. So I actually start at that fully charged capacitor and then integrate to some other charge that's less than Q initial. And then I'm integrating from 0 to t because I called the fully charged capacitor is at t equals 0. So I integrate this, I get ln of Q evaluated from Q naught to Q. So this becomes ln Q over Q naught. And then the other side is equal to negative 1 over RC times T. So I'm going to do the same thing as I did before, where I put an E here so that I can cancel out my ln. So I'm going to cancel out the ln there. So now I'm left with Q over Q naught is equal to E to the negative T over RC. I'll move my Q naught to the other side, so I have just Q of T is Q naught E to the negative T over RC. Okay, so this is our equation for the charge on a capacitor in an RC circuit as it is discharging. So now we have to find the current again, so we can just take the derivative of this equation to find the current. So we've got dq dt. We're going to take the derivative with respect to dt of q initial e to the negative t over rc. So this comes out to q naught negative 1 over rc e to the negative t over rc. And we can rewrite q. Remember, q naught is equal to q final, which we said was the capacitance times the EMF of the battery. So we can rewrite q naught as c times e. And then we have a 1 over RC here, negative 1 over RC. And so our c's cancel. And we're left with e to the negative t over rc. So we have negative e over r, e to the negative trc. And now what is this negative ER here? So we said before that ER is our initial current, but we have a negative here. So all that negative means is that now our current is moving in the opposite direction as when the capacitor was charging. So we can just rewrite this as I of t. We can just ignore the negative sign in our equation and just understand that the current is just moving in the opposite direction. And then we can just write our equation for the time-dependent current like this. So again, let's look at these two equations. So here we have the current. So the current is that I is e to the negative t over rc. Now, it's a little bit confusing here because it looks like the current is sort of increasing, but if we just plot the magnitude, that's because they used negative there. So if we just plot the magnitude of the current, it starts at I naught, and then it decreases to 0. So it might be a little bit easier to think of the plot like this. You can obviously see that the magnitude of the current is decreasing. Okay, and then the charge also exponentially decreases since we have that Q initial e to the negative t over rc equation. So both of these are exponential decays now. All right, so just a few things about the power in an RC circuit. So these are the same as in our previous lectures, but now we also have the rate that power is stored in the capacitor, and the total power supplied by the battery is given by this equation here. Okay, now let's do some examples. So our first example is a 10 mega ohm resistor. So mega is 10 to the 6. So a 10 mega ohm resistor is connected in series with a 1 microfarad capacitor. So we've got a battery here, we have our resistor, and then we have our capacitor. Actually, let me redraw that. Okay, so we have a 1 microfarad capacitor and a 10 mega ohm resistor, and the battery has an EMF of 12 volts. Before the switch is closed at time t equal t, the capacitor is uncharged. Okay, what is the time constant? So that's easy. All we have to do is multiply the resistance and the capacitance. So the time constant, tau, is equal to RC. So that will just be equal to our 10 mega ohms. Mega is 10 to the 6. So 10 mega ohms times the capacitance, which is 1 microfarad, so that's -6 is micro. So we see that our time constant, the 10 to the 6's cancel out. So we just get 10 seconds is our time constant. So now we want to know what fraction of the final charge, QF, is on the capacitor at t equals 46 seconds. So let's just first write down our equation for the charge. So we want to know what fraction of the final charge here is on the capacitor after 46 seconds. So the way we could do that to find the fraction of the total charge, if we divide the charge at time t equals 46 by the total charge, this will give us the fraction of the total charge that's present. So that is just equal to 1 minus e to the negative 46 seconds divided by RC, which we found was 10 seconds. So we can just plug into our calculator 1 minus e to the negative 46 over 10, and that is 0.99. So the fraction of the total charge, you can say, is either 99% or 99 over 100, or you could just say 0.99 of the total charge. So the capacitor is almost fully charged after 46 seconds. Okay, so we'll just say that that's our answer there. Now, what fraction of the initial current is still flowing at 46 seconds? So let's write our equation for the current. So that was I initial e to the negative t over RC. So what fraction of the initial current? So the fraction of the initial current is the current at 46 seconds divided by the initial current, that's the fraction, is e to the negative 46 over 10. So this comes out to 0.01. So that is our fraction. We could say that that's 1%, 1 over 100, whatever you want. All right, so now we're going to discharge the same capacitor. So the resistor and capacitor of example 26.12, so that was the one we just did. So we had the battery, we had our resistor and capacitance, that was 1 microfarad, 10 mega ohms, and this was 12 volts. Okay, so they're connected like before. The capacitor has an initial charge of 5 microcoulombs. So we'll say that our initial charge is 5 microcoulombs, and is discharged by closing the switch at t equals 0. So now when we discharge, t equals 0 is that second we close the switch. At what time will the charge be 0.5 microcoulombs? So Q of what time will be equal to 0.5 microcoulombs. Now remember, when we're discharging a capacitor, we take out the battery. So this is what our circuit looks like now. So this is part A. So let's write our equation for the charge on a capacitor as it's discharging. So we have Q of t is equal to Q initial, e to the negative t over RC. So we're saying at Q of some time, the charge is equal to 0.5 microcoulombs. So we're going to write that down. So we have 0.5 microcoulombs is equal to the initial charge, which is 5 microcoulombs, and then e to the negative t RC. So our 10 to the 6s with the microcoulombs will cancel out, so we don't have to worry about any 10 to the negative 6s. And now we just have to find t, right? Because we already found RC. We know that RC, the time constant, is equal to 10. So now we just have to solve for t. So what we're going to have to do is a little bit of algebra and some logs. So let's move the 5 to the other side. So divide both sides by 5. And then what we're going to want to do is take the natural log of both sides. So we're going to do ln of 0.5 over 5 is equal to ln of e to the negative t over 10. So the ln of e to something, this becomes, remember for logs, you can take the power outside. So that just becomes ln of e, but ln of e is just 1. So this is just 1. So now we have ln of 0.5 over 5 is equal to negative t over 10. So ln, let's actually move the 10 over here. So let's move our negative and our 10. So multiply both sides by negative 10, and we get negative 10 times ln of 0.5 over 5. So plug that into your calculator, and this comes out to 23. So after 23 seconds of discharging this capacitor, we're left with 0.5 microcoulombs on our capacitor. Okay, now we want to know at this time, what is the current through our circuit? So we have T equals 23, and we're just going to plug that into our equation for the current. So let me add a page. Okay, so now we have T is equal to 23 seconds. Our equation for the current through a discharging capacitor is I initial e to the negative t over RC. So this initial I, if we look back at our equation when we solve for it, we can rewrite our initial current as Q naught over RC right here. So let's rewrite I as Q naught over RC. So Q naught was 5 times 10 to the negative 6 coulombs. R times C is still 10. And then e to the negative 23 seconds over 10. So just plug this into your calculator, and you will get 5 times 10 to the negative 8 amps. So this is obviously a very small current because our capacitor is almost fully discharged. Okay, now let's go on to another. We have one more example with this stuff. So here we have a 12 microfarad capacitor is charged to a potential of 50 volts. So we have a capacitor that's 12 microfarads and discharged through a 225 ohm resistor. So that means that the potential supplied by the battery is 50 volts. How long does it take the capacitor to lose half of its charge? So we're discharging now. So the equation for the discharge of a capacitor is this. So we want to know, how long does it take to lose half its charge? Now we don't have the initial charge on the capacitor, but it doesn't matter because it's just saying half of whatever the initial was. So we can just write that as 1/2 since it's just basically a fraction like we previously did. So when the current charge is 1/2 of the initial charge, what is the time of that? So we just have to find T here. So we can plug in R times C. So let's get an equation for T before we plug any numbers in. So the first thing we're going to do is, again, take ln of both sides. So that becomes ln of 0.5 is equal to negative T over RC. We can multiply both sides by negative RC. So we get that T is equal to negative RC ln 0.5. And then we can plug things in. So negative R was 225. C was 12 times 10 to the negative 6. And ln is 0.5. And the natural log of 0.5 is going to be negative. So you'll get, at the end of the day, a positive time. You don't want a negative time. So this comes out to, if you plug all this into your calculator, this comes out to 1.87 times 10 to the negative 3 seconds. So it loses half its charge very quickly. Okay, so for this one, we have to think back. Add another page again here. So we have to think back to our unit on capacitors. And we want to know how much time it takes for the capacitor to lose half its stored energy. So the stored energy in a capacitor, you can write as the charge on the capacitor divided by 2C, right? So that was an equation we did in like chapter 24, I think. So we can substitute this Q for our equation, our time-dependent equation of Q. So we can rewrite this. So like the time-dependent energy stored is Q initial e to the negative t over RC squared divided by 2C. So this becomes Q initial squared e to the negative 2t over RC. So I'm just distributing out that squared over 2C. All right, so now let me just rewrite this. I'm going to put my Q naught squared 2C and then e to the negative 2t over RC. So I can see that this here is the initial stored energy. So that is actually my initial stored energy. So I'll call that U naught. Now, since I'm not looking for the how much energy it actually is storing at that moment, again, I'm just looking for a fraction. So I can write my equation for stored energy like this. And I'm just saying, well, what time will half of its stored energy remain? So I can write that as 1/2 is equal to e to the negative 2t RC. And then I just have to solve for t now. So again, I'm going to take the log of both sides, the natural log. So I'll have ln of 0.5 again. Then I'll have ln e to the negative 2t over RC. That becomes negative 2t RC. And then I can switch things around a little bit so that I get t by itself. So I have negative RC over 2 ln of 0.5. So let's plug some things in a little bit. So we have negative 0.5 from the 1/2. Then we have the resistance was 225 ohms. The capacitance was 12 microfarads. And then we just have the ln of 0.5. And this will all be equal to the time. Again, ln of 0.5 is going to be negative, so you'll get a positive time overall. So plug this into your calculator, and this comes out to 0.936 times 10 to the negative 3 seconds. Okay, so that was a little bit more challenging of a problem since you had to think back to the capacitors and sort of use a little bit of freedom here to get that equation. Okay, so that's the end of chapter 26 and our material for today and our material that will be on the midterm. So again, I know that this is like everybody's least favorite chapter, so it's okay if you feel like you don't like it that much. Again, don't hesitate to come to my office hours if you have any questions about any of the material that will be on the midterm. And good luck, and I will see you guys on Monday.